Hello, let's continue with electrochemistry, looking today at quantitative electrolysis. Our lesson objective is to understand the use of electrolysis quantitatively using changes in electrode mass. So continuing very logically from our discussion last time about electrolysis and what it can achieve using electrical energy to drive a chemical reaction that otherwise might not take place, we can do this in terms of a quantitative analysis, which, if we recall, it's to do with determining amounts of samples. So in this instance, we can measure the mass of substance produced at an electrode during electrolysis proportional to the following things: the strength of the electric current and the time through which you pass this electric current through the electrolysis system. So if we think about what we discussed in terms of an oil rig cat, where oxidation occurs at the anode, reduction occurs at the cathode. The positive is the anode, so we have negative anions moving towards the positive anode to be oxidized. Lose the electrons, electrons flow through the system, where our positive cations move to the negatively charged cathode, where they are reduced and they gain the electrons. So essentially, that's what we're measuring. We're measuring the mass of the substance that's produced at the electrode. So being a quantitative analysis, we can get some numbers going. So here's a good little equation if we're talking about the strength of the electric current and the time through which it's passed. We're talking in terms of the charge. So we're measuring the charge in coulombs, and it's going to be dependent upon the current through which we pass through the system. So the current in amps being generated from that power source, and how long we pass it through, which is in seconds. So I need to do some conversion if we're given these in minutes or hours, making sure our units are consistent. So these are all, what we're looking at today, quantitative electrolysis, is all based on some laws proposed by an English scientist called Michael Faraday. So let's have a look what old mate Michael was talking about. So his first law, he proposed that the mass of elements deposited at an electrode, so if you think about your cations being deposited onto the cathode, the mass that's deposited is directly proportional to the amount of charge that can be passed through, where we know that the charge is a result of the current and the time. And the second law, which we'll go into in depth in a little bit later on, the amount of charge, which we call Faradays, we'll introduce that momentarily. So the amount of charge needed to discharge 1 mole of an ion at an electrode is equal to its valency. So therefore, how much charge? Is it a 2 plus? Is it a 3 minus? Is it a 1 plus? The valency of that species. So let's talk about this Faraday's constant that we introduced very briefly just there. Electrochemistry involves redox reactions. So we have the transfer of electrons. So what this Faraday constant is describing the fact that 1 mole of electrons, or similarly monovalent ions, so +1 or -1 ions, carry a constant amount of charge called the Faraday's constant, where 1 Faraday is equal to 96,500 coulombs per mole. So we can use this to determine the amount of charge needed to deposit a certain amount of our substance during an electrolysis. So for example, here's 2 questions. You might want to pause now and have a look. How much charge does it take to deposit 1 mole of copper in the electrolysis of copper nitrate? How much electricity is needed to produce 1 mole of oxygen in the electrolysis of sulfuric acid? So have a think about what we've been talking about. 1 mole of electrons carrying so much charge. Consider how many electrons are in the equation. Let's have a talk about the answer now. So essentially, if our copper ions, to deposit 1 mole of copper, well, the stoichiometry of that, it requires gaining 1 mole of electrons. So if 1 mole of electrons carry a constant amount of charge, then this quite simply just requires 1 Faraday of charge. So 96,500 coulombs, or you could say 1 Faraday. The other one, a little bit different. This time, where to produce 1 mole of oxygen, there's 4 moles of electrons during this oxidation reaction. So as there's 4 moles of electrons released, it requires 4 Faradays because 1 mole carries a constant charge. So 4 moles will carry 4 times that to give us 4 Faradays of charge, or 386,000 coulombs. So what have we got here? We can calculate the amount of substance that is produced during electrolysis. So if you want to generate a certain amount of substance, you can do some calculations to work out how much charge you need to apply to this system. So we can use the value of F, Faraday's constant, to determine the mass of substance deposited at an electrode, or conversely, the volume of gas produced at an electrode, using the idea of the molar gas volume, the fact that 1 mole of gas will have a given volume at a certain temperature and pressure. Let us take a look at these kinds of questions. Calculate the mass of copper deposited at the cathode during electrolysis when we have 1.5 amps flows through molten copper bromide for 20 minutes. So we want to see how much copper we're getting produced on that electrode there. So look, if you want to give it a go, we've got all sorts of concepts now. We can work out the amount of charge with our equation here. Q is equal to I times T. Just remember your T's in seconds. And then we know that 1 mole of electrons has a constant amount of charge, which is a Faraday. So if you want to give it a crack, give it a red hot try, give it a pause, and we'll check it now. So there's a few steps that are involved for us to do. So the first thing we got to do is we need to consider the reduction half equation that's occurring at our cathode. So look, we got copper 2 ions. So our half equation, we're going to have Cu2 plus liquid because we're molten, and it's going to be gaining those 2 electrons, and we're forming copper solid. This is really important because we need to know how many moles of electrons we're dealing with. So then we've got to look at the number of coulombs to deposit 1 mole at the electrode. Well, let's have a look at how many electrons we have. We have 2 electrons. So to deposit 1 mole, we would need 2 Faradays. So we would need 2 times 96,500 coulombs, and that would give us an answer. If I very quickly get old faithful the calculator up, 96,500 times 2 gives us 193,000 coulombs of charge, because this reduction requires 2 moles of electrons. So now, how much charge did we actually put through this system? Well, our charge is equal to the current times by the time. We have, I might do this up here actually. We have a current of 1.50 amps multiplied by 20 minutes, but we've got to get that into seconds. Very important that our time's in seconds, so let's multiply that by an extra 60, so as to get our minutes into seconds. 1.5 times 20 times 60. So we've only charged 1,800 coulombs of charge through this system. But we've set up here, it takes a lot more than that to deposit 1 mole of our copper solid. So we're going to have a lot less than a mole of copper deposited. So let's work out how much mass we're actually going to be producing by using a simple proportion. So if it requires 193,000 coulombs for 1 mole, but we've only produced 1,800 coulombs, let's work out what that is as a fraction of each other. And then if it takes 1 mole, 1 mole requires that much, we can just multiply it by its relative atomic mass. You know, essentially using mass is equal to the number of moles times by molar mass, where our number of moles is going to be that ratio of how much charge we've put through. So our relative atomic mass, I might just see if I can free up a little bit of space here. Relative atomic mass is 63.5 grams per mole. So let's plug all this in the calculator. 1,800 divided by 193,000 gives us a decimal multiplied by 63.546, gives us an answer of 0.593 grams. So quantitatively, we're determining how much mass we're going to be producing at the electrode based on how much charge we're supplying to this system, which is a very useful thing to be able to do. Righto, so there we go, 0.593 grams of copper. So what I got here is I got a really useful simulation that I'm going to run us through now. I'll pop a link down below if you want to check it out, of course. So look, in this one, there's a few options. Let's just run an experiment. So let's run that experiment. We were using a molten, but let's deal with an aqueous solution. So let's say we've got copper electrodes, and then we have copper solution. So look, this is what a electrolysis might look like in the actual lab outside of just our diagrams. I might make it a little bit bigger there. So let's set our current. Let's set the current twice as much as what we had before. So we were dealing with 1.5 amps. Let's set it to 3 amps and have a think if you might be able to work out what that's going to do based on this relationship we've been talking about, what that's going to do to the mass that is deposited. We'll set it for 20 minutes and we shall turn it on. So look, we have the positive anode. This is where our oxidation is occurring. So our copper ions are losing electrons. The electrons are flowing through the system, like that, taking the long way around. And it's losing mass because these copper ions are undergoing oxidation. And there's a cool little microscopic view that we can explore here. So let's have a look at this one. So we have oxidation at the anode. These copper atoms are being oxidized to copper ions, moving into the electrolyte, and the electrons are moving up. And that's obviously showing us that loss of mass that is going to be occurring. We can see the electrode losing mass. So then it flows through the system. I won't look at these, it's just showing the electrons passing through via the metallic bonding model in those metal wires. And then we get to the negative cathode, which we can see is very much gaining mass. So let's have a look at what's going on here. So over here, we have the reduction equation. We have the copper ions gaining the electrons, or gaining the 2 electrons to form the solid copper. And we can see that we're gaining mass on this electrode as this reduction is occurring. There you go, you can see it's getting bigger in size. So this is a result of, you can see here, we can see the little copper ions moving through the solution here, going from the positive anode towards the negative cathode. And then at the end of our quantitative electrolysis, we can see that our weight difference, our negative cathode there, has gained 1.18 grams. It started at 10 grams, we've gained 1.18 grams, which is twice what we had over here. 0.593, multiply that by 2, you're going to end up with, give or take, 1.18. And that makes sense because we're using twice as much current, so we would expect twice as much of the copper to be deposited. And that all goes back to old mate Faraday here. The mass is directly proportional to the amount of charge, and if we're increasing the current, we're going to be increasing that charge. Fantastic. So look, that's a useful little simulation there. You can run all sorts of experiments. How do you reset it? Reset. All sorts of metals you can play with, all sorts of solutions. You can get a little bit more complicated with some standard reduction potentials that we haven't looked at yet. But yeah, I'll pop a little, little link in the description below. So let's finish off here by looking at another useful thing that we can use electrolysis for, which is for determining Avogadro's constant using this relationship F equals LE, where F is our Faraday's constant, L is Avogadro's number, and E is the charge of just a single electron. So one electron has experimentally been determined to have a charge of that many coulombs, a very small amount. We don't have to worry about how they've got this value, just the fact that we've got it, and it's a constant. So, I mean, I don't think this is too illogical, but essentially, let's go over here, I'll write some stuff up. If F equals LE, so if we have the charge of one electron, which is 1.60 times 10 to the power of, let me just double check, don't want to get it wrong, minus 19 coulombs. Minus 19 coulombs. And then we've said that Faraday is the charge of 1 mole of electrons. Well, if you got 1 electron and you multiply it by Avogadro's number, which is how many are in a mole, well then obviously you're going to get the charge of a mole. So if you get that and you multiply it by Avogadro's, let's just do this for the sake of making sure everything adds up. So if you plug this on your calculator, which I might as well do, I've written that completely wrong. I've forgotten a whole bunch of zeros, 6.023 times 10 to the 23. And then we multiply that by that. And what we should end up with, 6.023 times 10 to the 23 multiplied by 1.6 times 10 to the minus 19. We end up with, give or take, a bit of a rounding error here, but I might just do the old approximate 96,500 coulombs. Pretty significant rounding error in there, just because we're simplifying all these big numbers and that's rounded to begin with. But my point still stands. If you've got 1 electron charge and you multiply that by a mole, you're obviously going to end up with a mole of electrons. But this is useful because we can use it to experimentally determine Avogadro's number. As Faraday is the charge of 1 mole of electrons, if we rearrange this equation to make L equal to the, L the subject, we end up with Faraday's constant divided by a mole of electrons, and that will give us Avogadro's number. So let's look at how we can determine this experimentally. Essentially what we want to do is we want to first measure the mass change in electrodes, where the cathode increase is due to the deposit of the metal, and the vice versa for the anode decrease, what we observed over here. But experimentally, when we're using masses, we tend to use the decrease in the anode as opposed to the increase in the cathode. Theoretically, they should be the same number, but practically, not all of those metal ions, quote unquote, stick onto the cathode just through the nature of the experiment. Whereas you're going to get a much more consistent result to what you'd expect theoretically by measuring that mass loss. And like I say, they should be equal in quantity nevertheless. So all that to say is just use the decrease in the anode. So let's consider the electrolysis that we just did, where we have a current of 3 amps for 20 minutes, and we saw that we had 1.18 grams of copper removed from the anode. If you want to pause and see if you can use this data to experimentally use this relationship to determine what the value for L will be, go for it. We'll have a talk about it right now. So let's have a little think about what's happened. Let's first calculate the amount of charge that has passed through. So let's consider again our equations. Ce2 plus 2E minus goes to copper solid. I should put some states in here. What are we? Let's just say we're aqueous. The question didn't specify, but I'm specifying now. Calculate the quantity of charge that is passed. So Q equals I times T, where we said we had 3 amps, ran for 20 minutes, and multiply that by 60 to get that into the correct amount of seconds. 3 times 20 times 60 equals 3,600 coulombs of charge. So we can now use the mass change as a ratio of its molar mass. So to deposit 1.18 grams of copper requires 3,600 coulombs. So to deposit 1 mole of copper, we can use a ratio and go the molar mass, so the mass of 1 mole, and work out that relative to how much we actually deposited, multiply that by the amount of coulombs. But then we've also got to take into account how many electrons have been removed. So in this instance, we've removed 2 electrons. So we've got to multiply that by half to get our mole of copper. So look, we plug all this in, we end up with a value of, divided by 2, value of 96,864. I'll just keep all those figures there, which is looking pretty close to 1 Faradays of charge, because that's what we're calculating, the charge on one mole of electron, which is why we multiplied it by 1/2, because our value up there was for 2 electrons. Now, experimental results always have a degree of experimental error, but if we keep going through, we can now use our relationship up here, F equals LE, to determine experimentally what Avogadro's number is. So we said we could get L is equal to F over E. So let's do that. So Avogadro's number will be our experimentally determined Faraday's constant divided by the charge on 1 electron, which is the constant. So we plug this in, 96,864. We divide that by our charge of our electron, which we said was 1.60 times 10 to the minus 19. 1.60 times 10 to the minus 19. Plug all this in the calculator. Lots of calculating because, you know, we're doing a quantitative analysis, so we need lots of numbers. We end up with a value of 6.05 times 10 to the power of 23, which is pretty close experimentally to Avogadro's number. Now, you know, we would expect a degree of error, again, being a experimental analysis, but we can see we're using our quantitative electrolysis to experimentally determine Avogadro's constant. And that concludes our look at quantitative electrolysis, where we stated and applied the relationship between Faraday constant and the Avogadro constant and the charge on the electron, F equals LE. We calculated the quantity of charge passed during electrolysis using Q equals IT. We looked a lot at the mass. You can also do the volume, which we didn't go into too much detail, but you know, using the same concept, using the concept we've looked at before of the molar gas volume. So the fact that you know that a mole of any gas has the same volume, you can use that relationship to determine the volume. And then we describe the determination of the value of Avogadro constant by an electrolytic method right at the end there. Tasks, pause, work through them if you like some extra consolidation, and that brings us to a conclusion on quantitative electrolysis and electrolysis more broadly. From here, we'll look at a different kind of electrochemical cell. So we've been looking at electrolytic cells. We're now going to move into the galvanic cell. So I look forward to that next time. See you later. Have a good one.